This is lecture 2 of our Mathematics for Architects course. This week I'm going to be talking about intervals, Cartesian coordinates, functions, and sigma notation. And again, I'm talking in an empty classroom, so I'm going to be talking more quickly than I would otherwise do so. First, let's talk about intervals. A subset of the real numbers is called an interval if it satisfies two rules. Rule number 1, it needs to contain at least two numbers, and rule number 2, it doesn't have any holes in it. So, for example, the set of x such that, this vertical line means such that, x is a real number and x is strictly greater than 6 is an interval. I've tried to draw a picture of this interval. Starts at 6 and it goes all of the way to the right, all of the way to infinity. Because the number 6 is not in this set, we draw an open circle at 6. This set has at least 2 points in it. For example, 7 is in the set and 8 is in the set, so rule number 1 is satisfied. And there's no holes inside the interval. As soon as we start at the left point and we go all of the way to the right, then there's no holes in it. So this is an interval. The set of all real numbers x such that x is between -2 and 5 is an interval. There's at least 2 numbers in it. 3 is in this set, 4 is in the set, and there's no holes inside this set. For this set, the endpoints -2 and 5 are both in the set. To show this in the picture, we draw a filled-in circle. This set is not an interval. X such that x is in the real numbers and x is not equal to 0. Why is it not an interval? It's not an interval because it has a hole in it. There's a hole at 0. A finite interval can be classified as one of 3 ways. It could be closed, half open, or open. It's closed if it contains both its endpoints. It's half open if it contains one of its endpoints but not the other one. And it's open if it does not contain any of its endpoints. So, for example, here are the 4 different types of finite interval. Number 1, we could look at the x such that x is strictly greater than a and strictly less than b. And there's the picture on the right. This interval is open because the endpoints a and b are not in this set. We have a nice notation for open intervals. We write rounded bracket a comma b rounded bracket. If instead we use square brackets, square bracket a comma b square bracket, then we have a closed interval. That's the set of all real numbers x such that x is greater than or equal to a and less than or equal to b. This interval is closed because it contains its endpoints. And then in the bottom 2, we have half open intervals. One of the endpoints is in the set and the other one is not. An interval could also be an infinite interval. And if it's an interval, it could be either closed or open. It's closed if it contains a finite endpoint, and it's open if it's not closed. But there's one exception to this rule. In order to make higher mathematics work, in particular to make a type of mathematics called topology work, we need the rule that the whole real line is both open and closed. Here are 5 different types of infinite interval. First, there's the open interval between a and infinity. And then the second one is the closed interval between a and infinity. Then the open interval between -infinity and b, the closed interval between -infinity and b, and then finally the open interval from -infinity to infinity. That just means the whole real line. That's open and it's closed. Sometimes we might want to combine 2 or more intervals together, and we do that using the union notation which I introduced last week. For example, the closed interval from -8 to -2, union the closed interval from 2 to 8 is shown here. This is not an interval because it has a hole in the middle. For example, 0 is in between -8 and 8, but 0 is not in this set. Briefly, I want to talk about Cartesian coordinates. I trust you're familiar with these from high school. Point in a two-dimensional plane, we can describe using two numbers. First, we need two axes. The blue axis here is called the x-axis, and the red axis is called the y-axis. The point where these two axes cross is called the origin. This is the point with coordinates 0, 0. And then we can describe the point, the position of a point P, say, by measuring how far do we go to the right from the origin, and then how far do we go upwards. If we start at the origin and we go to P, we need to go right 4 units and then up 3 units. So P has Cartesian coordinates 4, 3. And for the same reason, Q has Cartesian coordinates -2, 4. We go to the right -2 units, so that's the same as saying we go to the left 2 units, and then we go up 4. The set of all points in the two-dimensional plane, that's all of the points x, y, where x and y are real numbers, is denoted by r squared. We have x, that's a real number, and we have another real number y. So we've got two real numbers, real number, real number. That's why we call it r squared. For example, let A be the point 2, -1, B be the point 3, 1. Draw the triangle OAB. Well, we can plot the point 2, -1, that's just here. That's A. We can plot the point 3, 1, just here. This is the point B. O is the origin. Connect these together, we get a triangle. Draw the region of points which satisfy x is between 1 and 3. Just look at part of this first of all. Just look at x equal to 1. That's a vertical line, the vertical line of all the points where x is equal to 1. So it's x. So it's xy is 1, 0, or 1, 1, or 1, 2, or 1, 1.1, or 1 point pi, or 1 point something, 1 comma something. It's a vertical line. We also have a vertical line x equal to 3, and then we're interested in all of the points which are between these two lines. So everything between the two lines. Draw the region of points which satisfy x is between 1 and 2, y is between 1 and 3. Here we're going to have 4 lines. X is equal to 1, x is equal to 2. That's 2 vertical lines. And we're going to have 2 horizontal lines. Y is equal to 1 and y is equal to 3. This is y is equal to 1, this is y is equal to 3. We're interested in everything that's between these lines. So that's going to be a rectangle. We can measure the distance between 2 points in two-dimensional space using the Pythagoras theorem. The distance between a point P1 and a point P2, and we denote this distance by 2 vertical lines, P1, P2, 2 vertical lines. This is the hypotenuse of a triangle, and we know from Pythagoras how to calculate that. So you can understand that the distance between the point P1 and the point P2 must be the square root of x2 minus x1 squared plus y2 minus y1 squared. For example, calculate the distance between the point 1, 3 and the point 4, -1. Put the numbers into the formula, and I'll leave this for you to check, and we end up with 5. The third chapter for today's lesson is functions. We're going to be writing things like y is equal to f of x. Here, f is going to be our function. X is our independent variable. We're going to be able to choose a value for x. And then after we've chosen the value of x, y will be determined. So y will be the dependent variable. What is a function? A function from a set D to a set Y is a rule which assigns a unique element of Y to each element of D. The set D of all possible values is called the domain of f. The set Y is called the target of f. And the set of all possible values of f of x is called the range of f. If we have a function with domain D and target capital Y, we can write it as f colon D arrow Y. So, for example, we might have the function f from the real numbers to the real numbers with the formula f of x is equal to x squared. Or a different function, we might have f from the open interval between minus infinity to the closed interval from 0 to infinity with the same formula f of x is equal to x squared. How is this a different function? Well, the formula is the same. It's x squared in both. The domain is the same. R is the same as the open interval from minus infinity to infinity. The difference here is the target. The target in the first function is all of the real numbers. The target in the second function is just the closed interval between 0 and infinity. So this is two different functions. We can think of a function like this. We can think of a function as just a collection of arrows which point from the domain to the target. Now, some of the points in the target will have arrows pointing at them, and some of the points in the target will not have arrows pointing at them. If we collect together all of the points which do have an arrow pointing at them, this is the range of f. Or we might think of a function as a machine. Some machine that we put a number into the machine and then we get another number out of the machine. Let's talk about some functions and domains and ranges. First of all, y is equal to x squared with domain the open interval between minus infinity and infinity. What possible values can y take if x is a real number? When we square a number, we always get a positive number. Y can be any number between 0 and infinity. We can make y equal to 0 by choosing x equal to 0. We can make y equal to 1 by choosing x equal to 1, and so on. We can make y as big as we want by choosing x really big. So it's the closed interval between 0 and infinity. Second function, y is equal to 1 over x. What's the biggest possible domain that we could use for this function? We can't divide by 0, but we could divide by any other number. So the biggest possible domain would be all of the real line except x equal to 0. And then the range would be the same function. All of the real line except y equal to 0. Function number 3. Y is equal to the square root of x. We can't take the square root of negative numbers if we're working in the real numbers. So the biggest domain that we could use would be the closed interval between 0 and infinity. If x is between 0 and infinity, then y is also going to be between 0 and infinity. Function number 4. Again, we can't take the square root of negative numbers, so the biggest domain we could take is minus infinity to 4. What's the value of y? Well, first of all, if we put x equal to 4, it's going to be square root of 4 minus 4, square root of 0 or 0. So 0 must be in the range. If we take x as a negative number of large size, let's say minus 1,000, y would be square root of 4 minus 1,000, or square root of a big number, which is a big number. Y could be as big as we want. So the range is going to be between 0 and infinity. Function number 5, y is equal to the square root of 1 minus x squared. Here, x must be between minus 1 and 1. Otherwise, we would be doing square root of a negative number. What are the possible values of y? Well, let's look at x at minus 1, at 0, and at 1, and let's see what we have. Minus 1 and 1 are the endpoints, but 0 is in the middle, and that might tell us something interesting. If x is -1, we have square root of 1 minus -1 squared. That's y equal to 0. If x is equal to 0, we get square root of 1 minus 0. Square root of 1 is 1. If x is equal to 1, then again we get y equal to 0. If x is between 0 and 1, or between 0 and -1, we're going to get some number that's between 0 and 1. So the range is going to be the closed interval from 0 to 1. 3 more functions, 3 different functions. They're different because we're using different domains. Y is equal to x squared with the domain from 1 to 2. If x is between 1 and 2, then x squared must be between 1 and 4. Next function, y is equal to x squared with domain closed interval from 2 to infinity. If x is between 2 and infinity, then y must be between 4 and infinity. Function number 8, again, y is equal to x squared, but now the domain is the closed interval from -infinity to -2. Because if we take a negative number and we square it, we get a positive number. So again, y must be between 4 and infinity. And a final 2 functions, y is equal to 1 plus x squared. If x is between 1 and 3, y must be between 2 and 10. These are half open intervals. And the final function, if y is 1 minus the square root of x, and x is between 0 and infinity, then y must be between -infinity and 1. I'll leave that one for you to think about. The graph of a function f is a set of all points contained in the point xy which satisfy the equation y is equal to f of x. For example, graph the function y is equal to 1 plus x squared over the interval, closed interval from -2 to 2. The first thing I'm going to do, step 1, would be to make a table of xy points which satisfy the equation. Going from -2 to 2, I could do look at -2, at -1, at 0, at 1, and at 2. And then just to understand this a little bit more, let's look at 3 over 2 as well. If x is -2, y is 5. If x is -1, y is 2, etc. I want to plot these points on some xy axes. Here they are. For example, this is the point where x is 3 over 2 and y is 3 1/4. And then step 3, draw a smooth curve through these points. This is the graph of the function 1 plus x squared. Now, no, not every curve that you can draw is a graph of a function. The graph we've just done, y is equal to 1 plus x squared, is on the left. Note that every vertical line between -2 and 2, or whatever our domain is, intersects the graph at most 1 point. But if I had a circle, then some vertical lines, like the one I've drawn, would intersect this circle at 2 points. This tells us that the circle is not the graph of a function. Because a function can only have one fx value for each x in its domain, that means that a vertical line can intersect the graph of a function at most once. That tells us that a circle cannot be the graph of a function because the vertical line I drew on the previous slide intersects the circle at 2 points. Actually, if a is in the domain of a function, then the vertical line x equal to a will intersect the graph f from d to y only at the point a, fa. My next idea is piecewise defined functions. Sometimes we can use a different formula to define a function on different points. We can define a function using a different formula on different parts of the domain. So, for example, the function absolute value of x. If x is a positive number, we can define this to be equal to x. But if x is a negative number, we define this to be equal to -x. Or one that's a little bit more complicated. f of x is minus x if x is negative, x squared if x is between 0 and 1, or 1 if x is greater than 1. And we can draw the graph like this. Let I be an interval, and let f be a function with domain interval I. F is called increasing on this interval if we always have that f of x1 is strictly less than f of x2 for all points x1 and x2 which satisfy that x1 is strictly less than x2. And f is called decreasing. It's almost the same, but we just change one thing. We change less than to greater than. So for example, this is an increasing function. It's always going upwards. If we take 2 points, let's call this one x1. The left one is always x1 and the right one is always x2. And then measure their values. And it doesn't matter where we choose x1 and where we choose x2, as long as x2 is bigger than x1. We always have that the function at x2 is bigger than the function at x1. This is a decreasing function, a function which is always going downwards as we move from left to right. This function goes up, down, up, down, up, down, up, down. This function is not increasing and it's not decreasing. Functions are sometimes even and they're sometimes odd. Let me just remind you that the even numbers are the numbers 2, 4, 6, 8, 10, etc. And the odd numbers are the numbers 1, 3, 5, 7, 9, etc. We define an even function as a function which satisfies the rule f of minus x is equal to f of x for all x in the domain of f. And we define an odd function to be a function which has the rule that f of minus x is minus f of x for all x in D. So for example, x squared is an even function because, and the way we show this is we start with f of minus x and we see what we get. That's minus x squared, or x squared is equal to f of x.
Hi hocam.
The function x cubed is an odd function. Why? Again, start with f of minus x. What do we get? We get minus x cubed, or minus x cubed, which is the same as minus f of x. For an even function, look at the picture graph. Even functions have the property that the right-hand side is the mirror image of the left-hand side. We can imagine drawing a mirror on the y-axis. Imagine there's a mirror down the middle. The left side is then the mirror image of the right side. For an odd function, the rule is that we could rotate the graph by 180 degrees, and then it would be the same. All odd functions have this property. For example, is x squared plus 1 even, odd, or neither? Let's start with f of minus x and see what we get. Go through the calculation and we get f of x. That tells us that f is an even function. Is x plus 1 even, odd, or neither? This time, instead of looking at every possible value of x, I'm just going to pick one number. I'm going to pick the number 2, and it's negative, minus 2. G at minus 2 is minus 1, and g at 2 is equal to 3. And these numbers are not connected. G of minus 2 is not the same at g of 2, so it's not even. G at minus 2 is not the same as minus g of 2, so it's not odd. That tells us this function g is neither even nor odd. Next, very quickly, I'm going to talk about some of the common types of functions. The linear functions are the functions f of x is equal to mx plus b. These are functions which have where their graphs are straight lines. The power functions are the functions x to the power of a, where a can be any real number. For example, if a is equal to 1, we just have y is equal to x. That's also a linear function. If a is equal to 2, we get y is equal to x squared, a equal to 3, a equal to 4, etc. But it doesn't always have to be positive numbers. We could have a equal to minus 1, because x to the power minus 1 is the same as 1 over x. Or we could have fractions. A is equal to a half, for example. X to the power of a half means square root of x. X to the power of 1/3 means cubed root of x. This is x to the power 3 over 2, and this is x to the power 2 over 3. A polynomial is a function which looks like number, power function plus number, power function plus dot 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 plus number, power function plus number, power function plus number. The domain, by which I mean the largest possible domain that we could use of a polynomial, is always the whole real line. If we do polynomial divided by polynomial, then we get a type of function called a rational function. For example, 2x cubed minus 3 divided by 7x plus 4. That's polynomial divided by polynomial. So that's a rational function. The exponential functions are the functions of the form a to the power x, where a is a real number, a is strictly positive, and a is not equal to 1. The largest possible domain of an exponential function is also the whole real line. The opposite, or the inverse, of an exponential function is a logarithmic function. We write y is equal to log base a of x if and only if x is equal to a to the power y. And again, a has to be a real number which is strictly positive and is not equal to 1. Next, I need to talk about angles. There's two ways to measure angles, using degrees or using radians. I want to introduce the idea of radians. Imagine we have a circle of radius 1. And let's suppose I wanted to measure this angle, which I'm drawing in orange. If we're using radians, what we do is we measure the angle around the outside of the circle of radius 1, and we say that is the angle in radians. So, for example, if I have a semicircle, we know that the angle inside the semicircle is 180 degrees, and we know that the distance around the outside of a semicircle of radius 1 is pi. So that means that 180 degrees is the same as pi radians. Divide both sides by pi. 1 radian is the same as 180 over pi degrees, or divide both sides by 180. 1 degree is the same as pi over 180 radians. 3 common angles we will be using. 45 degrees is the same as pi over 4. 60 degrees is the same as pi over 3. And 90 degrees is the same as pi over 2. If we're using degrees, we have to draw a little circle next to our number to tell us we're using degrees. If we use radians, we don't use any symbols. Anytime you see an angle which doesn't have a little circle, it means radians. In calculus, we must use radians. When we get to part 4 of this course, if you see an angle, I will definitely be using radians. Why? Because calculus doesn't work with degrees. The trigonometric functions. There's 6 trigonometric functions: sine, cosine, tangent, secant, cosecant, and cotangent. And we define them using a circle. Let's suppose we have a circle of radius r. Let's suppose we have a point on the circle, and we measure the coordinates of the point as x and y numbers, and we measure the angle between the x-axis and this green ray, and we call that theta, either using degrees or using radians. We define the first two, cosine, using these numbers. Sine theta is always y divided by r, and cos theta is always x divided by r. After we've got these two, we can define the other four using sine and cosine. Tan means sine divided by cos. Sec means 1 divided by cos. Cosec, there's two different common ways to write cosec. If you want to have a three-letter symbol, you can write CSC. If you want something that's easier to pronounce, you can write COSEC. It's completely up to you which one you use. That means 1 divided by sine, and cotan, or COT, means 1 divided by tan. Now, note that because we can't divide by 0, tan theta and sec theta are only defined when cos theta is not 0, and cosec theta and cotan theta are only defined if sine theta is not 0. Let's look at some common angles. Let's start with 45 degrees, which is the same as pi over 4. I have a triangle here, base 1, height 1, and then by Pythagoras, the other side must be the square root of 2. And I want to use the angle at the bottom left. Sine is going to be the height divided by the hypotenuse, 1 divided by root 2. For cos, it's 1 divided by root 2. Then after we've got those two, we can get tan as sine divided by cos. Sec is 1 over cos. Cosec means 1 divided by sine, and cotan means cos divided by sine. We can get the other four straight away. Next, let's suppose I start with an equilateral triangle, a triangle where all three sides are the same. And let's suppose we say that each side of this triangle has length 2. And then I want to take this triangle and I want to cut it in half and just look at the left part. So then I have a triangle of base 1, hypotenuse 2, and using Pythagoras, the height of this triangle must be root 3. Then we can calculate sine of pi over 3. That's the same as sine of 60 degrees. Height divided by the hypotenuse, root 3 divided by 2. Cos pi over 3, or cos 60 degrees, is base divided by hypotenuse, so 1 divided by 2. And then after we've got those, the other four we can get using sine and cos. The graphs of sine and cos look like this. Our final chapter for today's lesson is about sigma notation. Let's suppose we want to add lots of numbers together. And then instead of writing something like A1 plus A2 plus A3 plus A4 plus A5 plus A6, etc., all of the way up to plus AN, we have a neat way of writing this. We can write this as capital sigma from k equal to 1 to n, AK. This large symbol is a Greek letter, it's capital sigma. The k equal to 1 on the bottom tells us that when we do our sum, we start at k equal to 1, and the n on the top tells us that we finish when we get to k equal to n. So, for example, 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared plus 9 squared plus 10 squared plus 11 squared, we can write as the sum from k equal to 1 to 11 of k squared. Or f of 1 plus f of 2 plus f of 3 plus dot 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 plus f of 99 plus f of 100, we can write as the sum from k is equal to 1 to 100 of f of k, and so on. I'm going to leave the rest for you to check. You just note that we don't have to start at k equal to 1 if we don't want to. We can start anywhere we wanted. For example, we could start at k equal to 4. Now, let's suppose I want to find a formula for 1 plus 2 plus 3 plus 4 plus 5 plus dot 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 plus n. That's a formula that we're going to need in part 4 of this course. Now, what I'm actually going to do is I'm going to start by finding a formula for double this, 2 times the number that I really want. And I'm doing that because I want to write it like this. The first one I'm writing as the same order, 1 plus 2 plus 3 plus 4 plus 5, etc. But the second of these, I'm going to write in the opposite order. Instead of starting at 1 and going upwards, I'm going to start at the biggest number and go downwards. N plus n minus 1 plus n minus 2, etc. And why am I doing it like this? I'm doing it like this because if we add the numbers above each other, I get 1 plus n. And then I get 2 plus n minus 1. 2 plus n minus 1 is the same as n plus 1. And 3 plus n minus 2 is the same as n plus 1. These are all n plus 1. I get n plus 1 plus n plus 1 plus n plus 1 plus n plus 1, etc. How many n plus 1s do I have? Well, the first one is number 1 and the last one is n. I've got n lots of n plus 1. So n multiplied by n plus 1. This is double the number that I really want. To get the number that I really want, I'm going to divide by 2. The sum of k between k is equal to 1 and n must be n multiplied by n plus 1 divided by 2. Two similar formulas, but which are more difficult to create. The sum of k squared is n plus 1, 2n plus 1 over 6, and the sum of k cubed is n plus 1 over 2, all squared. When we get to part 4 of this course, in the last few weeks of term, we are going to need these formulae. And that is the end of today's lesson. Next week, I'm going to start part 2 of this course, which is about geometry. I'm going to talk about polar coordinates, conic sections, and three-dimensional Cartesian coordinates.